All right, let's start off the unit with some notes on relations and functions and what those mean. So a relation is a set of paired input and output values. So we kind of use the idea of a machine. So if we give a machine an input, it's going to give us an output. So a relation is describing like what that looks like. And so here we have 4 different pairs, and this arrow is describing like how that set is created. So for example, with these ordered pairs, we pair them up one next to another. So 3 is the input, -1 is the output, 4 is the input, and here 4 is also the input, and you're getting a different output. Yeah, so ordered pairs you've seen before. They're just points. A table is the same deal, except we're summarizing it just in a different way. So I'm copying down the same numbers, noticing that 4 has 2 different y values. We're going to hop back to that later. A mapping diagram, you may have seen before, is 2 groups, kind of. These are called the domain and the range. And we're going to put down all the numbers that show up. So -3, 3, and 4. We're not going to duplicate. Just 1, 4 is fine. You'll see why in a second. I'm going to put down the unique numbers that show up over there. And then you put these arrows. So just like this arrow up here, we're going to include those in our picture. So we have -3 to 4. We have 3 to -1. We have 4 also goes to -1, and it also goes to 3. All right, so it wasn't necessary to write these numbers twice. Like 4, we only needed it once, and has 2 arrows coming from it. All right, so the domain is the set of those inputs, and the range is the set of the output values. So as you can see, the input is kind of normally the x, and the output's the y. So we can also draw a graph with these things. So if I have my ordered pairs over there on the left, I'm just going to go ahead and plot those. So I go -3 first and then up 4. That gets me here. 3 to the right and down 1 would be here. 4 and down 1 is here, and 4 and up 3 is right up there. All right, so do not connect the dots. This is the entire graph. There's only 4 pieces of data. Okay, so those are relations, but a function is a special type of relation where each input only has exactly 1 output value. All right, so let's look at some representations and see what that might look like, what a function is and what isn't a function. So here with this first one, let's think, is that a function? Does every input have exactly 1 output? The answer is no, because this 2 here, it sometimes is mapped to -3, and sometimes its output is 3. So there's some uncertainty, right? X equals 2 has 2 y values. And that goes against the definition of a function. A function has to be what's called well-defined. Every x that you put in, it needs to be mapped to only 1 y value. So this one here, let's check exactly that. So -7 goes to 14. 9 goes to -7. 14 goes to 7, and 7 goes to -7. So we can see that we actually don't have any duplicates here. So of course, every x value has only 1 y value. So this is yes. Okay, and then this table here, take a moment and think, is this a function? It's not. It's not a function because x equals 4 has more than one y value. Oh, sorry, that should say output too, by the way. So a function, it needs to be given like step by step. It's not very smart. All it does is it knows what you give it as an input, and and that goes to exactly one output. If there's any sort of confusion, like 4 being, it's not clear. It's not clear if 4 should go to -1 or to 5, and that's what makes that that uncertainty is what makes it not a function. So yeah, this is no. Okay, let's keep moving. So a little bit more about domain and range. We normally write it in what's called interval notation. So it's great for values that are between two numbers. So we did these inequalities before, right? We had this is bigger than or equal to 0. This one we even used compound inequalities. And we had all this. And those were ways to describe that set. That's an inequality. We want interval notation. So, by the way, these arrows go on a little longer. It's not super clear, but these do go on forever. Interval notation works like this. You read it from left to right. So you say the first number I come up with is 0. And then I go on forever. So that's infinity. If you touch a point, we give it a bracket. And infinity can't be touched, right? It goes on forever. So we have parentheses here. Infinity and negative infinity always have parentheses. Okay? So in the middle here, we start at -2 and go to 3. We touch 3. We don't touch -2. So that would be the interval notation for that segment. And over here, it goes, we always do left to right. But we have an arrow on the left. So it's like almost, we don't even really know where to start. So it does go though, it's pointing to negative infinity. It's going to keep going. And then it'll stop at 1 and it will not include 1. All right, so these ones are kind of like your open circles or your less than, greater than. Whereas these ones are more your closed circle and with your or equal to's. Okay? So that's in kind of like a 1D standpoint, but we have to be able to look at graphs and say what's the domain and range. So here, this is asking, is this a function? And we have a test called the vertical line test. And what you do is you make them purple lines here. You draw these lines everywhere on the graph, and you ask the question, do those purple lines, does a single purple line hit the graph more than once? And yeah, that very first one did. In fact, all of them did. But if you ever have this double intersection or triple or more than that, it's just not a function. Because that breaks the idea, right? This is x equals 2 we're dealing with down here. Let's erase these ones. This is saying that if you plug in 2, it goes to 2 different values. It's unclear. So no, it's not a function. But it still has a domain and range. So remember, the domain is all of the x values. So if we're looking at the red graph, we ask, where are those red values on the x-axis? So this one here. Like, where is the red function? Where does it lie? Can you plug in a negative number? The result is really, it's all the positive stuff, including 0. So if you're wondering what the domain is, the question you ask is, can I find an x, can I plug in a value into this graph. Like, does it go anywhere, right? It wouldn't make sense to pick, -2 over here. That's not in the domain. It doesn't go anywhere, right? So the domain is just the values that you are able to plug into the function, okay? And the range is the outputs, right? It's supposed to describe what y values does this graph hit. So now we look here on the y-axis and say, all right, where does this red function go? Like, can it reach here? Can it reach down here? Can it reach here? And because this graph does go on forever, the range for this is all reals. It's everything. So we say -infinity to infinity. Because, yeah, it is possible that you could hit the graph down here. It's possible to hit that tick mark if you make the graph long enough, right? If you make it long enough, it'll eventually hit that, So range is the y values, domain is the x values. So just jumping straight to that over here, the domain is going to be, here we're not going to use intervals because we have just a collection of points. So we'll use those set brackets again. And I'm going to list all the x values that are hit. And I'm also going to list all the y values that are hit. So -2, 2, and 3. I only list them once. Do we think this is a function? Here? Normally functions are like connected and like they go on forever, but this one, you can still ask if it's a function or not. And it is. It's a function because every x value has a y value that it goes to, just exactly one. Okay. Vertical line test also passes there too. Speaking of vertical line test passing, anytime you draw a vertical line, it only hits the graph once, right? So this is a function. The domain is, again, looking here on the x-axis, are we allowed to plug in all those values? Like, does it show up on the graph somewhere? And the answer to this is yes. Yeah, everything. You can plug in anything you want. It doesn't matter. You can plug in 0, right? Everything has a place to go. Like if you plug in this number, it goes, plug in this one, it's mapped or it's placed up there, right? Every single mark you can make on the x-axis, it has a place to go. So we call that, we say all reals, or we just say everything, -infinity to infinity. Now, the range. The range is the set of y values that can be reached by the function. Okay, so we're no longer thinking horizontal, we're thinking vertical. Can all the points in that gray, can they all be hit? And up here, like, yeah, like we hit, like if we have a little point that's traveling on this graph, it can hit everything in here, right? Because you just have to plug in the right x value, and these points here, that shaded in green, it's everything. But as we're bouncing around with this point, we're not actually hitting all the y values, are we? We are missing all of this, right? We don't hit any of that. So the range doesn't go that far. It starts at -3 and goes up to infinity. Because you can't get -5 to come out of this function. Like when you plug in a number, there's no way it can be down there at -5. So it's a restricted range. Like it's not everything. The domain is not restricted at all. All right. So let's do some function rule stuff real fast. I don't want to bore you too much with this. I might just do one of them, then give you time to do the other during a pause. I'll give you the answer. A function rule is representing an output value in terms of an input value. So a little bit different. Normally we said x was the input, y was the output, but we're going to change y. So this is equal to y, but we're going to write it as f of x, which means a function of x. So it's a function, and it's got x's in it, right? So it's some expression with x's, and it's a function. It's a bonus. So you can also plug stuff in for x too. So let's just dive into this real quick. So if we want to plug in 5 into the function, we put a 5 everywhere. And I'll give you that this is 75 plus 3 is 78. So the because if we didn't change the notation, if we just used the regular one, we would just get an answer like y equals 78. And while that's great and it's the right answer and everything, it doesn't really give us much info. Like if you were showing it to a friend, like just saying this doesn't really build a lot of context. But this statement here is really nice because it tells you 3 things. It tells you what your input was, 5. It tells you what you plugged it into, which function you used, f. And then it gave you the output. So it's really a lot better to use this notation when we're talking about functions. So we get all this info in a summary. You could also plug in -2. So anywhere there's an x, just like up here. Anywhere there's a 1, you put a 1. So this is -30. So -27. So there's our summary for that one. So we plugged in -2 into f, and it returned, it gave us back -27. Okay. So go ahead and pause the video and try G. Try and figure those out. All right. So I'm not going to explain much of it. I'm just going to go ahead and just show the work here. Once you get a hang of it, it's not bad at all. So this is saying that you plugged in -3 into G. G is just another name. You could use any letter you want. We like to use F, G, and H. But you plugged in 3 into the function, and it gave you -16 in return. And you can do the same for any number. Right? So I would do 9 divided by 3 first, because it's telling us to multiply by 7, but also divide by 3. So I want to divide by 3 and get 3, and multiply that times 7 is 21. So however you slice it, this is what you get. So yeah, talk about in science, you talk about independent and dependent variables. Well, the independent variable is x, the input. We choose that. We choose the input, but then the dependent variable is what depends on what x was. Okay. So we got just a little bit here. So tickets to a concert are $35 each plus a handling fee. What's the function rule modeling the cost of tickets? Well, let me ask you this. If you buy 2 tickets, thinking of this as kind of like a machine, if we give it, so this is F. If I say to you, hey, I want to buy 2 tickets, we need to have a function that tells us how much it's going to cost. So if I told you I wanted 2 tickets, you would say, all right, well, 35 times 2 is 70 $70 plus the handling fee. So I think it'd be like $72.50. It just as an example. That's what's happening. But we have to find out what F is. I don't really care about this specific example. I want to know what physically happened to the 2 to make it into 72.5. And if we kind of go back to what I said, 35 times 2 was a big part of it. So The function, it takes the input 2, multiplies it by 35, but then it's got the handling fee as well, and we had to add that on the end. So that's the function rule. Multiply the number that comes in by 35 and add the handling fee. So let's go ahead and that's part A. I mean, that is the function rule. However you want to think about it. Now, for tickets, we just make x4. So we multiply it times the cost of the ticket, and then you add the handling fee. So it should be $142.50. So, but there's the whole story, right? F of 4 is that dollar amount. So it reminds me that I plugged in 4. So, this is the answer, the whole thing, all of this. Okay, let's make another function. So we have this pattern, and it's asking us about perimeter. So maybe we should start off by saying, what's the perimeter of all of these pictures? So then we can maybe notice a pattern. I think that's a good idea. So all these rectangles are the same. So I can do this sort of thing. Remember, perimeter is the distance around. If you were a bug and you had to go around the edge on that black line, or around the whole rectangle, that's the perimeter, the distance that you go. So we would go 6 plus 1 plus 6 plus 1. I think that's 14. And if we add another rectangle, I think we add 2. And then we add 2 again. And then we add 2 again. So those are the perimeters. Those are the distances around. Okay? But it's our job to figure out, well, what's the function rule? Like, what's the equation for this? So it's clear that you kind of have to add 2 every time. So what I was thinking for this one was, we know that 6 and 6, like, those show up in every single picture, as long as we have at least one. So that's, to me, is kind of like our fixed amount, 12. And then we add a certain amount based on how many rectangles we have. And because it goes up by 2 every time, I think it's 2x. So let's test that, though. If we have x equals 1 rectangle, the perimeter should be 14. And it is. If x is 1, f of x, or f of 1, is 14. Let me write that over here. So this is just giving me some confidence, right, that I wrote down the right function rule. If you plug in 1 to my thing, you get 14. And if you look at the picture, it's 14 as well. Okay? So there's a lot of ways you can come up with that too. But we definitely want a function rule, because I don't want to have to draw out 15 rectangles, that's for sure. So I will go ahead and plug in 15 as the input. And then we're going to get eventually, this is 42. 30 plus 12. So if I have 15 rectangles, then my perimeter around would be 42. Pretty large. All right, I hope that gives you a better glimpse of what a function is. It's kind of like this machine that we give an input, it spits out an output. What we talked about at the beginning, or right here, it's about exactly 1 output. So a relation isn't a function if it takes 4 and puts it at multiple different y values. Like, every x should go to one place. So this example here, it wasn't a function, because if you plugged in 2, it wouldn't know what to do, right? So, all right. So these sets, this is kind of the trickiest part, to be honest, of the unit. So keep looking at these, keep studying these, and we're here if you have any